Hi, my name is Feng, and today I'll be talking through a machine learning project on predicting cirrhosis from patient data from Mayo Clinic trials. And the goal of this analysis is to develop a well-performing machine learning classifier that can predict whether a patient will suffer from cirrhosis in the future based on patient's available data. So the data set contains a diverse mix of data types and some categorical variables, also some quantitative variables. And there's some key clinical features such as bilirubin, albumin, and stage, which is directly tied to how the patient fares in the future after registration. And also we have some numerical variables such as N days, and that will provide us with timeline information on the patients. And we also have some demographic factors such as age and sex, alongside some biochemical and physiological markers such as cholesterol. We can drop ID of our patient's data because this will not be used in our prediction model. And we have the index number on the left in the data set that will work well for us already. And then we can actually use some variables to characterize and group the features, such as the quantitative features, such as age and end days. And we can put drug, sex, the spiders, edema status into categorical features. And most importantly, we mark our target variable, which is a binary variable stage, in which we'll process into a binary variable later on in our data processing steps. So let's now move on to checking the data sets on missing values and duplicated values. So we can see that for some numerical values, also some categorical values, we have some missing values. We will deal with them later. And after we check the duplications of our data set, we did not find any duplicates. So that's pretty good. And here's a brief summary of all the variables can be used in our data set. And now we can move on to the pre-processing part. So for missing values, we can actually fill in all the missed values, the null values with 0, because that will not introduce significant bias later in our machine learning model construction. And this will also mark that there's some missing values there for the categorical variables. And then the most important part is actually to encode our target into a binary variable. So we are sort of using an if statement using a NumPy function where. And so we are so there are 1, 2, 3, 4, 4 stages for the patients. We're actually replace stage 4 as positive, which is patient will get cirrhosis, and the rest 1, 2, 3 into 0, which is means negative. And we are also we will pick some numerical variables and put them into X, which we'll use in our machine learning model construction. And next, we're dealing with the skewness of the distribution of our variables. So we are actually here to use the log transformation to make the variables normally distributed. And let's now deal with outliers. So outliers can influence model predictions because they will disproportionately represent the data. And here we can use two-keys rule. So we will handle outliers outside the IQR interquartile range and flag them. So for these outliers, we have identified we can use Winsorization, which captures extreme value without removing them. And this will make sure that the data set remain robust and while mitigating the impacts of extreme values. And here for categorical variables, we are using dumb encoding to put them into our a model or regression as predictors. And we have selected about 7 predictors in our model for them to predict the Y, which is the stage we just encoded. And to see the balance, we want to see like how many of the data sets actually will represent patients that will get cirrhosis. And we can see that it's about 0.3. And it's a little skewed, and we will have to deal with the imbalance later on in our model building. So here's a correlation map that shows correlations between different variables, also our dependent variable stage in our model, in our regression. So we can see that with stage, we can see some really high value, like moderately high values such as 0.3 and maybe 0.27. Not too high, but they show greater correlation with our response variable stage. These are maybe bilirubin, albumin, and endase. We'll keep them in mind, and later we'll assess our model. So let's officially move on to experimental setups of our model building. So here we have constructed a workflow to ensure robust and balanced training and testing. So we are splitting the data into training and testing sets using an 80-20 ratio. And we use a standard scaler to make sure that numerical feature is standardized, and it will help us in future feature scaling and such as logistic regression. And we are using synthetic minority oversampling technique, SMOT, to ensure that data is balanced and the model does not favor the majority class. And now let's begin our official model building. The first one, we will use a standalone decision trees classifier. So we'll also use the standard scaler, also SMOT, to deal with imbalances. And so we end up with a decision tree model that gives the accuracy of about 64%, a sensitivity of 58%, specificity of 68%, and it's doing moderately well, but we want to check if there are other better models out there. So we can construct a PyCaret, a local classifier, workflow or pipeline to determine whether there's a better models for our prediction. After running the codes with the same setup, we have a 80%, 20% training testing split, and the target is a binary stage variable. Also, we have a cross-validation of 5 folds to ensure robust model building. So this give us the best model called extra trees classifier, which has an accuracy of 75% with the AUC, area under curve, of 80% and precision about 65%. And there are other models available, such as random forest classifier, also the AlgaBoost, etc., but not as good as the extra trees classifier. And we want to check if this model really works. So we are studying learning curves of this. We can see the testing score, training score is really high, and we have the cross-validation score increasing as the training instances gets bigger. And for the feature importance plot, we can see that the endase, bilirubin, prothrombin, and albumin are the top 4 contributing features. To compare between the standalone decision tree model, classifier model and the extra trees classifier model is that the extra trees classifier outperformed the standalone decision tree classifier by improving accuracy from 64.3% to about 75.77%. And we also have improvements in precision and recall. And so we can see that PyCaret's automated feature engineering, hyperparameter tuning, and handling of imbalanced data significantly enhance model performance. And this extra tree classifier is an ensemble method, and it leverages multiple decision trees to capture complex data patterns, and that make it better performing than a standalone decision tree model. And that's the model we will use to predict whether a patient will have cirrhosis in the future. And thank you. That'll be all.